and I'm expecting some more call-ins, but let's just get started. So, good afternoon, everyone. My name is Handel Cui, and welcome you to the Current Power and Energy Seminar Series. Today, we are really glad to have Dr. Kristen Cetin with Michigan State University to present her most recent research for us. So her topic for today is advancing smart, sustainable, and grid interactive buildings in an era of COVID-19. Dr. Kristen Cetin is an assistant professor at Michigan State University in the Department of Civil and Environmental Engineering. She is a licensed professional engineer with over 10 years of experience in the construction, building, and building systems industry in both academia and the industry. Her current research involves a range of projects in the area of design, construction, and operation of sustainable and grid interactive buildings. She currently leads several major projects as PI funded by ARPA-E, A-Share, the Sloan Foundation, industry sponsors, and NSF, and is involved in other research sponsored by EPA, FAA, and state DOTs. Prior to MSU, she was a faculty member at Iowa State University. She received her PhD at UTexas Austin in civil engineering, worked as a consulting engineer at Simpson, Gumpertz, and Hesher in Washington, D.C. So audiences, if you have questions, feel free to type it in the Zoom chat box or raise your hand at the end of the presentation. So we have saved like 5 minutes for our questions. So Dr. Cetin, so I'll turn the presentation to you.
Okay, sure. Can you hear me okay?
Yes, sounds good.
Okay, all right. I guess before I get started, so I don't know everybody on here by any means. It's like teaching my classes. I can't see anybody, but I would say as I'm presenting, if you have burning questions or something, I'm happy to answer questions in the middle as well, whatever works for you all. The idea of this is to try to give you a little bit of my background. So I have some slides to talk about kind of my journey to where I am now, in the case that that's helpful for you as a student. And then I'm going to talk about kind of the motivations for some of this research, not just COVID-19 related things, but just smart and sustainable buildings in general. And then I'll talk about some projects and then the implications of COVID-19 and some of the studies initial studies we've done related to COVID-19 impacts on just the building industry and building research in general, because there's so many assumptions that go into working with buildings and occupants. COVID-19 has kind of turned everything over and changed everything about what we typically assume about buildings. And so that's what I'll try to talk about is some of the implications there and kind of the outstanding questions related to that. So hopefully this is interesting. Again, I'm here to try to make this interesting and answer questions. So if you have them, please feel free to say something. So I'll give you a little bit of background about myself first. I'll say that I never in my wildest dreams as an undergrad imagined that I would be a researcher or a professor, but here I am. So it's been an interesting journey to be here. I am from Maryland originally. I grew up there for 20-something years, went to University of Maryland, did my undergrad and master's. I graduated in 2008-2009 timeframe, which if you remember was a horrible economic challenge. So the jobs were quite limited, but I was lucky to get a job, but also work as a master's student when I graduated from undergrad. And then I tried out, I was planning to go and work in industry, and that's what I did do for a little while. I tried out working at different places as an intern, land surveying, construction, consulting, trying to figure out what to do, and ultimately enjoyed kind of the forensic engineering side of things. So trying to figure out what's wrong with buildings was really very interesting. So I ended up doing that for a little while. But before then, during my undergrad and master's, as well as between my undergrad and master's, I spent some time abroad I worked in France for a little while doing historical restoration. So this is some pictures of repointing of old buildings in Saint-Emilion. And we actually got to hand carve stones to replace stones that had fallen out of infrastructure. It was really interesting to learn. This was one of my favorites that we carved, kind of unique. So that was really fun. I also worked for almost 10 years with Engineers Without Borders at the University of Maryland chapter. We did several different projects that I worked on in Brazil. And this is one of them, a wastewater treatment system, construction of wetlands. Really enjoyed that. And also did some solar decathlon work. So these are some of the two first kind of participation that University of Maryland had in solar decathlon back then, close to the beginning of the solar decathlon kind of competition. So that was enjoyable, introduced me to a lot of building concepts. But then kind of worked for a little while in DC at Simpson, Roberts and Hager doing, I would call forensic engineering, building envelope consulting. They're most known for designing Epcot, the ball. So if you're ever there, the big dome there. So we did new construction. So things like going to buildings and telling the contractors what they were doing wrong, how to fix it. And then investigating challenges with buildings like, this is mold related issues behind wallpaper, impermeable surfaces. So that was really interesting to learn about those things. And then rehabilitation, often those were things that combined structural engineering related concepts and building systems concepts. So enjoyed that a lot. For some personal reasons, I had to leave the DC area. So I ended up working and going to UT Austin in the Building Energy and Environments group and working there for a few years doing my PhD. Also spent a little bit of time at NREL, National Renewable Energy Lab in Colorado in their residential building group. And kind of got my foot in the door with research related things. And then ended up at Iowa State University in the construction engineering program, teaching construction engineering related courses, doing building related research. And now just this is my end of my first year at Michigan State. So greatly enjoying it, kind of a little bit different atmosphere, but that's been kind of my journey to where I am right now. In terms of research, I've always kind of enjoyed this idea of sustainability. A lot of that I think stems from some of these background experiences. But if I was to summarize it, and what you'll hear about in some of the research projects here is related to mostly buildings, but not all buildings. There's a lot of civil infrastructure that requires the same skills and knowledge as building systems, but just a different application. So that's why I kind of more in general infrastructure systems focus. So like I said, design, construction, operation of buildings to try to make them more sustainable. And so in order to do that, we have to understand the components of building. So energy and thermal performance, so how it consumes energy, how it interacts with the environment. And then interacts with the occupants. So occupants are really important to occupied buildings, because if occupants aren't comfortable, then we've lost the point of having a building in the first place. So that's important, something that's a big part of this study. And then their behavior. So what do occupants do? How do they interact with the environment? And how do we try to model and simulate and understand that for a typical building? And then there's the part that we can't control, which is the climate. This is a huge impact on HVAC systems, or heating and cooling for buildings. Big impact on comfort. Very important for us to be able to model and understand, and be able to understand the interaction of buildings with those climates. And all those kind of interrelate to each other, and then connect to, and this is definitely kind of a more recent and important topic, according to most sponsors at least, is the smart grid. So the electric grid, as it becomes more renewable, is important for buildings to be able to interact with that. So how do we do research in these areas? A lot of it is modeling, and often that modeling is accomplished in kind of combination with laboratory or field testing to validate those models. a lot of data analytics, so for doing data-driven modeling, those kind of things, and some risk assessment. So that's kind of all the interrelated things. But really, if we're going to summarize the main things we're working on here, it's a combination of building science, so understanding building systems and their interactions, with this idea that we have a more connected environment than we used to. And those combined together, we're trying to make buildings that are more efficient, they're more flexible and more interactive, healthy, productive, whatever you want to call it, just better in general, more smarter and more beneficial to the end user of those buildings. So that's the overall idea. In terms of kind of research capabilities, you know, beyond modeling and working with computers, I run these labs. These are 2 identical buildings that we use for parallel testing. So essentially you keep one building as a baseline building and the other one you change something about it and you assess the thermal impacts or the visual impacts or the energy impacts of that change. So these are really helpful in validating models and kind of full-scale testing of sensor systems, those types of things. So that's kind of the idea here. We automate the different systems, collect the weather data, indoor environmental conditions, energy use in these buildings to be able to assess performance. So we have a number of projects. I'll talk about one of them here that is ongoing in those spaces. So kind of in fun field in general, I'd say a lot of different applications. But before I talk about the specific topics, I think it's important to kind of provide some context here. And I may be kind of speaking to the choir here and understanding what these challenges are, but I do think it's important to discuss as this is ever evolving and just like the title of these, the presentation, there's things that happen that are completely unexpected that impact the building field. COVID-19 is one of those, for example, from a ventilation perspective and an energy consumption perspective. But then we also have things like climate, and climate is not something that we can necessarily predict per se on a kind of frequent basis, but we can look at long-term trends and try to understand what is it that we can do to adjust our buildings to make them more resilient and more sustainable. So that's what I'll talk about here for a few minutes and focus on energy related challenges because that really is kind of the main component of this research. So we think about electricity consumption as we grow in population, in number of buildings, and kind of looking at the historic trends and into the future. It's projected that we kind of will continue to increase our electricity consumption. Similarly with energy consumption, we'll kind of see these increasing trends. And if we consider what is the best opportunity or what's the best target to be able to identify ways to reduce or at least somewhat reduce that energy or electricity consumption, buildings really are a significant portion. So about 40% of our energy and about 74 or 75% of our electricity. And if there's not any other motivation to try to reduce this consumption, you know, we have plenty of recent events to remind us of some of the climate change related challenges. So, you know, the wildfires that are currently going on the West Coast, you know, we have a record number of hurricanes that have occurred recently this year before September. That have made landfall. We had, I came from Iowa, so recently the Iowa area had this major land hurricane with major straight line winds that devastated a lot of the infrastructure there. There's been record heat in Arizona this year and much of the Southwest, setting records that haven't previously been beaten in a while. And you know, we have some projects. We have a project right now working in Alaska where permafrost melt is a major issue. So you've got structural related challenges, energy related challenges in that area because of the changing climate. So if there's no better reminder to try to think about addressing some of these energy related challenges, that's certainly some of them. So beyond electricity consumption, so kilowatt hours in general, we're also looking at demand because buildings are the substantial consumer on the electric grid. it's important for us to consider their role in trying to make the electric grid more sustainable and more reliable. So this is a plot, this is from Texas, but it's general, kind of looks like this for all summer periods on the electric grid in the US, where we see this variation. And when it gets very hot, we get this kind of significant peak demands, and that in extreme climates, for example, in Texas, significantly increases electricity prices. It can stress distribution or transmission distribution on the grid, and also require kind of peaker power plants or plants that are less efficient than ideally we would like to use. So if we're trying to address this, again, buildings, at least based on some studies that have been done, are a substantial portion of this demand, this peak demand. So if we consider, if we go back here, this late afternoon around 5 p.m., we've got a combination of commercial buildings being used while people are still at work, combined with residential buildings as people return home and turn on their air conditioners, right? So it's not surprising that buildings would be a substantial portion of this peak load. So what do we do about it? There are some different options, and it's a popular kind of topic in DOE, for example, right now. We can either reduce our electricity consumption, so improve our efficiency, reduce our peak load, which is something that has been a focus in recent years, or we can try to be more interactive or dynamic and match our renewable resources more closely by adjusting not just how much is available to consume, but when our buildings are consuming energy. So this is what's happening in California, and likely will happen across the country moving forward as we get more solar energy, more renewable energy on our grid. We get kind of this, we call it the duck curve, kind of looks like a duck, where we get this reduction in the middle of the day, and then we get this, the big challenge is this ramp, so the significant change in electricity demand over a short period of time, and that's challenging if you're trying to provide electricity to meet that significant change for the electric grid. And then you get a peak that's higher than what the original peak would be because you've got more consumption during that period. And so these challenges, particularly the ramp, is something that we have to keep in mind as we try to make a more renewable and sustainable electric grid and buildings. And we have to do this all while considering that buildings are built to provide an environment that's comfortable for occupants, for the people that live in them and work in them. And as we spend 90%-ish of our time in buildings, and at least by historical trends, 70-ish% of that being from residential, we do have to make sure that if we're improving the sustainability of our buildings, that we're also considering thermal comfort, our visual comfort, the indoor air quality, indoor environmental quality, and particularly in some of the times where we've had natural disasters, these are particularly important. So what are the opportunities? What do we do about this, and what does this research relate to? We have seen a substantial growth in connected devices, Internet of Things, sensors over recent years, and I'll show a graph in a minute about that. And at the same time, kind of starting, at least a lot of it started during some of the economic recession money that was given out to support kind of economic growth. Saw a lot of growth in smart grid infrastructure, smart metering, those types of things. So we have more connectivity on the electric grid than we used to. So communication between our generation, our consumers, and our transmission that enables us to collect more data, and also enables us to have more dynamic interactions between these players that we didn't used to have. And so that's exciting because as we see these increase in connected devices, and this is just an example here that shows what's the growth in the reach of connectivity and the internet. It's exciting because that gives us opportunities we didn't have before to adjust and support renewable energy resources and adjust energy use and consumption of buildings in ways we weren't able to before. So here, this is just showing that growth that I mentioned. So we've gotten kind of over 50% of residential buildings have smart meters now. So that means we can monitor their energy consumption. We can interact with them, at least the ones that are two-way communication, in, like I said, in ways that we didn't used to be able to. So what do we do with research on this? This is a picture and some that shows kind of some of the areas that I work in. I'm going to touch on some of those projects, and then I'm going to talk about COVID-19 related implications of some of those assumptions and some of those efforts that we're working on. So you see a few different topic areas here: occupants, building envelope systems, smart appliances, HVAC systems, and then grid interaction. So I'm going to touch on a project for each of these that relates to those and some of the efforts we're working on. And if you're interested in more details, I'm happy to provide them. Just kind of wanted to give an overview of some of the things that I think are exciting and kind of interesting in this area at the moment. So these are some of the projects I'm working on, and I'm just going to touch on a few things for each of them. So this one is the first one. We've had a few projects, and we're now working on a third that I didn't have time to add here, but it's a DOE project. But some efforts to try to improve the adaptability of building systems and the building envelope specifically. So the barrier between the internal and external portions of a building. So right now, building envelopes, so our walls and our windows are very static. They don't change. Their properties are always the same. And we've generally accepted that that's the case. But the idea here is that the properties of those building envelope systems could be changed and adjusted to make them more ideal for the conditions that are occurring at a particular period of time. So the idea here is, can we build in elements into these systems that can be adjusted dynamically based on the conditions that they sense, to make it more energy efficient and make the occupants comfortable at the same time. So just kind of to show a diagram here of what we're currently working on. If you picture a typical building and a window, often there's shading devices on the interior. People want to adjust if there's sun coming in or not, but they're typically manually controlled. And so studies have shown that blinds or shading devices in general are never adjusted to their ideal conditions on a regular basis if they're manually controlled. But at the same time, blinds alone on the interior are not as energy efficient as trying to adjust penetration of solar energy into the building from the exterior. So what we're doing here is we have a multi-layer system of fenestration where we retrofit it onto an existing window and add electrochromic glazing on the exterior so that it's adjusted based on the external environment and occupant preferences. And then on the interior, we have a shading device. And so those two in combination are adjusted to try to optimize occupant comfort, visual comfort, so occupant visual comfort and thermal comfort, and reduce energy consumption. So that's something that we're currently working on. We've done a lot of modeling related to that and are now doing some laboratory testing, working on setting that up. So that's one example. Another one that we're working on right now considers kind of future scenarios of buildings and their impact of different types of demand response. So demand response being reducing energy demand when the grid requires it based on a signal of some sort. So the impact of demand response resources on transmission distribution investments. So the idea here is, if we have significantly higher renewable energy penetration and much more electrification of the grid, that means that we can't necessarily predict when wind is going to be available, and we can kind of predict it for solar, but there's also some variability there. So we need to have loads that are much more flexible and much more able to adjust themselves when needed to meet those demands, meet the loads that are available. So with this project, we're trying to figure out what kind of demand flexibility is possible for different types of building loads and which building loads are ideal for this. And so this just shows a picture of some efforts we've done to look at, this is large appliances and residential buildings, and what the loads look like over time, so that we can identify which loads are ideal for adjustment or demand response for different periods. And just as an example, here we see that refrigerator in the upper right hand or upper left hand corner represents a kind of a constant source of energy, but it's not very flexible. So it's always available, it's very reliable, but at the same time, you can't turn off a refrigerator for very long. So that represents kind of one type of energy resource. But then you look at, say, a electric dryer is a much substantially higher amount of demand when it's on, but the amount of variability in when those dryers are used is much higher. And so what we're trying to work on is figuring out how we can combine these types of available resources together to provide kind of our future grid the available resources it needs to be adjusted for different grid services to make it reliable, but also supporting different types of renewable resources. So that's what we're working on with this project. This one is interesting. We just finished it up, and kind of, I think, speaks to some of the future of electrification in general. So this is an airport, so we got the chance to work with the Des Moines International Airport to monitor energy consumption of what they have recently implemented as electrification. So they, instead of using gas-powered systems to support their airplanes when they're docked at their gates, they instead use electric ground power systems and electric air conditioners or preconditioned air systems. And so as a result of the implementation of electrification of these things, we were wondering, well, how much is this impacting what the electricity costs are? And as we move more towards electric grid that varies in demand or in available electricity use, and then also different types of renewable, well, not renewable, but different types of electricity cost structures. What are the implications for airports? So we looked at and monitored the gate use and the electricity use of these systems over about 6 months or so, tried to understand what the implications are. So we collected this gate use data and monitored energy consumption. And if we think about peak demands right now, gate electrification represents a very substantial portion of electric loads in the airports in general. And so if they consider in the future that we are going to have these, go back here, cost structures that are more focused on peak demands, that's something that's important for them to consider. And that goes for buildings in general as well, as we consider when buildings are consuming energy, knowing when these peak demands are is important. Okay. Next thing to talk about is kind of more high level, and that's associated with trying to model what the energy demands are in overall, like in a city. And so there's a number of challenges here that are somewhat interesting. And this is motivated by power outages and kind of understanding what the energy consumption is of an area as opposed to a particular building. So it's important to consider, since we do lose so much from power outages due to reliability or weather-related things. If we can better predict what the energy demands are of a city, then that helps us to understand maybe what the challenges might be moving forward. So what we worked on with this project was trying to assess in the future, what are these extreme conditions going to be? What's the peak temperatures going to be in the locations we looked at? So we looked in Texas and looked in Iowa to see what would we predict these extreme weather conditions to be, extreme heat in particular, since that's kind of the main driver for energy demands on the grid. So we worked with some climate scientists to develop these global climate models that represent spatial variation and temporal variation in energy or in weather conditions. And this is called a WRF model. So it's a forecasting model that has several different domains, and then also considers an urban canopy model. So that's a representation of the buildings in a city and their production of heat and their interaction with various different components of the weather. So we created this coupled WRF UCM model to try to understand at the city level how some of these extreme events might occur. So this is just showing a picture of what that type of simulation looks like and the variation spatially over a location. And this shows on the left what the model looks like without considering the city. And you see those kind of stars, those are locations within the city of Austin. And here you see when we consider what buildings and their interactions with that look like, we can see kind of a better representation of the spatial variation in temperatures. And so what we tried to do is then use that to create a model of the city scale energy demands and consumption. So it's just a diagram, but we visualized it in GIS to show kind of where the extreme consumption and demand are located within the city. So what we get from that is a model that tells us, this is the validation of that model, that tells us what the energy demands of the city are. And we can project that into the future based on the environmental conditions in the city and how that varies spatially. So that's some more like high level efforts, not building specific, to try to model energy. The last one I'll talk about, and then I'm going to talk about the implications of all these different things from COVID, which I think is kind of very unique and interesting to think about because it's not something that I think any of us would have anticipated might occur. And COVID-19 in particular has impacted this project, which focuses on occupancy, because we're supposed to be testing occupancy sensors, yet everybody's not where they normally are, nor are they following their typical routines. So what do we do about that? And what's going to happen? What do we assume? These are all very interesting things to think about. But occupancy in particular is something that it's hard to say as we move through this COVID-19 related challenges, what's going to happen. Are we going to go back to our normal routines? Or are we going to change them? Anyway, this project focuses on occupancy sensors. So what we're working on is trying to figure out a standard methodology for testing of occupancy sensor systems in residential and commercial buildings. So we want to try to understand what's the reliability of these systems so we can compare them, and what's their potential energy savings. So you might say, well, occupancy sensor systems already exist. The idea here is that we're trying to test occupancy sensor systems that would be more reliable, they're lower cost and more reliable than what we would normally consider. And unlike most occupancy sensor systems right now, which are connected to lighting systems, that's the main use of occupancy sensor systems, they would be connected to the HVAC system. So the heating and cooling system, we would adjust the heating and cooling system based on whether there's occupants there or not. And that represents a substantially larger amount of energy savings compared to lighting. So the interesting thing here to think about is occupancy. So right now in modeling efforts, occupancy is something that is generally considered to be consistent over time. So in energy modeling programs, standard considerations are that we, as occupants, are generally following a similar schedule regardless of our socioeconomic status, of our size of our family, same kind of thing. And that we thought was somewhat arbitrary, and we wanted to look into it more. So we've worked with this national data set called the ATUS data set to try to understand better how occupancy varies. And it's been very interesting to look at. We did some cluster analysis to look at differences in in occupancy profiles, and generally across the age groups. There's, of course, some variation, and there's also variation by income level, among other things. But in general, we see kind of a stay-at-home pattern, a work in the day pattern, a work at night pattern, and then some that kind of vary in between those things. And so this is very different from what's standardly assumed, which is more similar to this work during the day type profile. So you see here on the right-hand side, what we typically assume is this black line, and the red are the weekdays and weekends. Then we also see, if we look at 1, 2, and 3, and 4 member households, that it varies substantially, at least based on what we've calculated to, in those assumptions. And so, why do we care? We care because if people are at home more versus not, that substantially impacts how much energy savings can be achieved. So people that are at home all the time can't really get much energy savings if they're there, but people that are gone, you can get much more. So the question is, which type of household are we looking at, and is that important? What we've worked on currently is developing this occupancy simulation tool to allow other people to be able to use it. So this is just the procedure, but it's interesting to think about and to see. We get everything from a 1-member household, which the typical schedule, you'd only be able to save a few percentage points of energy savings, to something like a 4-member household where you get 30+% energy savings. So this is what the schedules look like. You get this stochastic occupancy schedule, and then you can see what these energy savings potential is. So anything from, you can see here the electricity and gas, and then total is right here. Our maximum threshold of energy savings as we get to the higher setbacks is around 20-ish% for some locations. So this has been really interesting to think about, and you see here too, you can get even higher when you have additional types of setbacks. But the question is, as we go forward with this testing, or go back here and go forward with this testing and continue, these assumptions for occupancy are based on historic data. And the question is, well, COVID-19 happened, and we no longer following anything close to what pre-COVID-19 related assumptions look like. The question is, well, are we going to return to those previous standard of living, the previous things that we've done, commuting to work, being home for X amount of time? Because it's fairly consistent across the years if we look at our analysis, but whether or not that actually will continue now that we've had this substantial change in lifestyle is a big question. And the other question would be, what are the implications of this? Is it a positive or a negative implication? So that's what I want to talk about here for the next few minutes, and then we'll go to questions. So as a result of COVID-19, what things have happened? And these are generalizations, but they're generally correct, I would say. Residential buildings, so people are spending more time at home, whether they're required to work from home or able. Certainly not everybody, but many. More children are at home, whether for personal reasons or otherwise. People are homeschooling, or schools are closed, or daycares are closed. More people are working at home too, again, by choice or not. And other people have lost jobs, and so they would be at home as well. And so the amount of time people are spending at home and the things people are doing at home is substantially different. Commercial buildings, so people are going to restaurants less, using sports complex less, if at all. Some office buildings don't have any people in them. Hotels, conference centers, public facilities, many of those are either closed or at minimum capacity. And so, from a residential standpoint, we've got more people at home. We're likely consuming more electricity. And from the commercial standpoint, we've got a lot of buildings that are not being used the way that they were designed. And this also has implications for the electric grid. So, the electric grid in general across different countries reduced energy consumption, at least for a while, because of this change in how buildings are used and people being at home, the question is, will our patterns of electricity use continue that way, or are they going to change or turn back to normal? What's going to happen? And that's hard to say, I think, as we kind of haven't gotten to the end of this yet. But let's talk about residential for a minute. This is something that we decided we would spend some time on to try to quantify. And we thought about it in two different ways. One is HVAC related and one is non-HVAC related. So HVAC being your heating and cooling system, and non-HVAC being everything else. So all of our electronics, our appliances. And we thought about, well, have we changed how we're using our HVAC system? Are we using it more? Are we keeping our house more comfortable because we're at home more? And from the electronic standpoint, are we using more electronics? Are we using our appliances differently? What are we doing different? You probably say, well, Dr. Cetin, of course we are. We're changing it because we're at home more. But our question was how much, and has that changed? And so we did some preliminary analysis. This is working with a data set in Texas that we've worked with previously that monitors single family homes energy consumption. And so it was really interesting. We compared multiple different years. This is just one example, comparing the same homes from 2018 to 2020, about a few hundred homes. And you see here in red, 2020 compared to 2018. And across every day of the week and month of the several months following COVID-19, and we're working on the others, but you see here that substantial difference, right, in the non-HVAC use. So 15% or more per day. In this case, for these are somewhat larger homes, about 2 kilowatt hours more per day per home. So that's important to us when we're thinking about assumptions for occupant behavior for energy savings. Same thing here when we're looking at non-HVAC. This is significantly higher if we look at January and February, which is that yellow and orange, compared to March, which was partially impacted by COVID, to April, May, and June, where they're all kind of centered around this kind of higher profile. 8 to 21% increase in energy or HVAC use, non-HVAC use, excuse me, during these periods. And then peak energy demand is also slightly higher, right? So yeah, this is important and different than what we've seen really ever in our lifetime, at least. And then we think about it from income level, and this is also different. So we see on the left here, at least based on our preliminary analysis, the lower income levels, and these are not low income, but lower income, don't have as much difference in what their energy consumption patterns look like compared to, say, kind of the upper brackets of income level by household. So that's interesting to think about too, in terms of an occupant behavior related implications. How are people changing their behavior? It seems like, it does have some impact, and your income level does seem to vary somewhat, at least across the data set we looked at. Then in terms of HVAC use, if you're familiar with HVAC use, so it really does depend on weather. So if we look at on the x-axis, this is temperature. And so we're normalizing this by temperature. And these look a little messy, but the point is, if you look at 2018 versus 2020, the 2020 bar, the line is translated up slightly in all of these cases. And the idea there is that per weather condition per day, we are consuming more energy per typical temperature conditions. So we are consuming more of both. And so what are the implications of this? And this is the end here. Things to think about and implications for this field in general in smart buildings is, so what will happen with work and post COVID-19? Are we going to have commercial buildings populated in the same way or not? And are our historical assumptions about occupancy valid? Do we need to change what we model? Do we need to change how we assume things? But I think the more exciting thing, and something that's been really interesting to talk with some collaborators about, is this mean that there's opportunities for improving our sustainability of our infrastructure? And I'll just give one example, and then I'll stop for questions. So there's been a lot of discussion about if, since buildings aren't occupied, you would expect that commercial buildings in particular should be reducing their energy consumption substantially. And while there is some, it seems that there's significant opportunity for more. So if we could better sense occupancy in our buildings, then we could better reduce that to make buildings more sustainable when things like COVID-19 might happen again in the future. So that's the presentation. Tried to keep it on time here, so I think we have a few more minutes for questions. I'll let you kind of lead the way on how you want to do this.
Thank you very much, Dr. Cetin, for the presentation. I know you are collaborating with Dr. Chen-Fei Chen, and without her invitation, we wouldn't have you presenting for us. So, does Dr. Chen, do you have any questions? Or
Oh yes, I think Professor Cetin has done everything you can think about, including my field. So very impressive, very impressive. I have a lot of questions, but I'll keep it short. One is demand response. We have been talking about demand response so many years, and still some areas or cities don't even have demand response program. For example, Knoxville, Tennessee. How are you studying demand response in terms of different than other, the incentive program? What do you think about this incentive? Demand response program?
You mean that, like, the current methods that are being used, if they're effective, or
you think what is the future for demand response? It's an important component, but it's like not many cities are adopting, or not many people know about it, and there's a lot of barriers. So what do you think about this demand response for the future?
So I guess I probably have an opinion. That I also read some industry reports that like survey the industry about demand response. So right now, most of the demand response is associated with commercial and industrial loads. But most of the reports that I read and like survey results from industry and utilities say, as moving forward, more of the demand response will be associated with residential buildings, because there's such an opportunity there. And in terms of how that's done, my understanding of what the reports say is, most of that on the residential side right now is related to HVAC systems, so direct load control, and then more recently, smart thermostats. And it seems like, at least based on what I understand, that the smart thermostat type effort, either bring your own thermostat or through incentive programs to give them to people, seems like a growth area. And then in addition to that, the other things that seem to be kind of leaders, electric vehicles, water heaters are the like next things, and then maybe in the future more smart appliance type things. Since like Energy Star, for example, now has optional options for appliances, things that consume large appliances, to be certified to work for demand response with demand response signals. So I think it's coming, but I doubt it's very soon. It's slow.
Yes, I think this is an important component, but still have a lot to study, because it involves human behaviors.
Yeah, you just got to mandate it, and then it'll be fine. But I doubt that's going to happen either.
Okay, my second question is related to COVID-19. Your analysis seems like higher income people spend as they use more energy. Is that right? And
actually, it's not something that we looked at so far. Probably, though, we have larger buildings, so I believe that's correct. In general, you've got kind of larger infrastructure per household.
Mm-hmm. So higher income people use more energy than lower income people.
I think so. Yeah, per household. Actually, that's not the metric that we
Okay,
did so
sorry,
far.
I was
It's just
jumping
more
ahead.
so. No, it's okay, but I'm sure you're right. I would guess that that's correct. So
Yeah, but do you observe, maybe it's not in your presentation, do you observe low income people stay home more or higher income people stay home more during the pandemic?
during the pandemic, I'm not sure we can say conclusively what that is, but so this is what I would guess, and this is based on like what we looked at some with the ATUS data that varies by income level.
Yeah.
So if we assume that that's correct, and we don't really have much way to validate it, but if we assume that that analysis is correct, then it is true that the lower income levels have a higher percentage of people that follow an occupancy profile that is close to like a stay-at-home profile. So more people are following or staying at home in that income bracket compared to others. So I would guess what's happening is that, at least based on what we see in that initial analysis, that there's not too much difference. It seems like it, compared to the higher income levels, that maybe the reason that's the case is that they already have people at home, and so they're not really changing much. I'm not sure, but it's a guess, but it could be something that could be investigated. That I would guess the higher income levels have more people that are gone for substantial periods of time during the day. But I don't know. That's a guess. I can't verify any of that at this point.
Okay, thank you. Anybody else have questions?
Yeah, thanks, Dr. Chan. I actually have another perspective about like the energy consumption of those low-income people, because they tend to live in buildings that are older with worse kind of insulation, and during summer they tend to consume more energy for cooling. So that may counter their kind of intention to save energy.
I would agree with you. So yeah, I mean, you're right. Generally you're gonna have older buildings, older appliances, older, not as well taken care of, most likely. So I would guess that would impact especially the HVAC side of things. I didn't put the figures up there for income level, but we didn't, for HVAC, we didn't see that much substantial like differences between income levels, maybe a little bit, but nothing that was real clear across the income levels. But we did see it on the non-HVAC side, so the anything except for heating and cooling. So
Gotcha.
yeah, that's where we saw more clear, I guess, differences. But yeah, again, it's preliminary. She'll need to look at it some more, but it was interesting to see, at least in the initial analysis, some differences.
Yeah. I have another survey I conducted in New York during the pandemic. Actually, higher income, we ask perceptions. So higher income people think they use more energy. Lower income people think they use less energy. So it's interesting to see their perceptions. And higher income people, of course, their houses are bigger, much bigger. But in reality, we estimate energy burden, we divide by their income and their energy bill. Actually, low income people pay more percentage wise. So again, this is involved with appliances and then household installations and so on. Now, of course, we are looking at proportion, not total amount of the utility bill. So the low income people definitely pay at least 3% more than the medium and higher income level. All right. Anybody else? More questions?
More questions?
Very interesting talk. Yeah, we'll talk more. Hope not.
All right.
Thank
well,
you.
It's nice to be here. Yeah, good to talk to you guys. If I can help with anything, let me know, I guess, or I can send you guys the slides if you want it as well.
Okay. Thank you so much.
All right.
Thank you very much, Dr. Cetin.
Nice to talk to you.
Nice talking to you.
Okay, take care. Thank you. Thank you for your time. Bye.